When my soils professor encouraged us to find a creative way to show that we've actually learned something this semester, I immediately thought of the mud pit behind our house. For months it's been plaguing us. So today we're going to take everything I've learned in 342 Engineering Behavior of Soils and do some tests to determine what exactly we have here and how we can fix it. So follow me. While we don't have a lab per se, we do have a makeshift field workstation that will help us identify what exactly we're working with. So our first step, of course, is to identify what type of soil, right? Silt, clay, etc. I'm no expert at this, but the folks at the county GIS are. So let's take a look at what we have here on their website. So for reference, behind us we have the mud pit, right? And behind that is the dam of the pond. As you can tell right here on the GIS website, there's the pond, right? And here we are right there. You can see this is a Baden Terrace complex, whatever that means. So I Googled it, and apparently it's a silty clay loam. Based on what I saw, that's definitely clay, and it looks pretty fine grained, so sure, silty clay, that makes sense. So anyway, what we want to determine is what's the water content of the soil, where the water table is, and if we are at quicksand conditions. So that's all a lot of math, but to help us out, I have created an Excel spreadsheet that we can just plug and chug. So let's pull that up and we'll get started on our first step. Let's go weigh it. Okay, so I'm gonna take the volume. It's a 5-gallon bucket. I assume it's 5 gallons, but we're gonna check the diameter, the inner diameter. $14 and math, 3/16. All right, so divided by 231. 6.379 gallons. For the purposes of this experiment, that's good enough. Yes. Cool. So now we need to take the weight. Jack! Hush, buddy. Good boy. Okay, now we need to take, we know the mass of both of these buckets, so we just need to know the mass of the sand. Oh! 63.2 pounds. Is cubed. Okay, great. We should have everything we need. I should note that there is some larger sand in the bucket. That's pretty big sand if you ask me. But like I said, this is an at-home, close enough kind of thing. So, all right, let's load up and go over to where we're actually going to be doing this. Okay, so Eli, my handy cameraman here and pretty awesome brother, pointed out that it says 5 US gallons all the motto of this, so my math was wrong.
It is called a 5-gallon bucket after all.
Well, I googled it, not all 5-gallon buckets are made equal. Let me double check my math before we go anywhere. So we're getting conflicting numbers here. Like I said, this is very this is back of envelope math, so we're gonna say that my volume is right. I mean, we're guessing anyway because we have, like, this is not pure sand. Just so you know, I am in fact level-headed, okay? All right, you can cut it. Okay, so first things first. Let's take a look at this handy dandy Excel spreadsheet I have. Let's come closer, please. So we have 2 buckets. One bucket full of sand that we collected earlier from the creek. Bucket number 2 is going to be what we put our soil sample in.
These things is because it's a lot of work to find what these are. I think one method for calculating rivets.
All right, so the first things we need to do is determine the volume of the bucket, bucket 1. This is bucket 1, this is our sand that we got from earlier. Determine the volume of bucket 1, the weight of bucket 1, and also volume and weight of bucket number 2, which is where we're going to put our soil in. We are using a bathroom scale here, and it's not exactly super sensitive. When we placed the bucket on the scale, it gave us a weight of 0. If we use a weight of 0, that's going to give us errors in Excel, so we're going to assume a weight of, we'll say 0.2 pounds, because why not? So volume of bucket 1 is 0.2. Volume of bucket 2 is 0.2. Volume we calculated earlier as 6.379 gallons, which is different from the reading on the bottom of the 5-gallon bucket. However, I triple checked my math, so we're going to assume I'm right because I'm never wrong. So we're going to assume I'm right and put in a volume of inches, or is this feet? We'll do inches. All right, now if you're following along from home, I am going to link this Excel spreadsheet, at least for the duration of the class, in the description of this YouTube video. So you can follow along and judge my math there. So anyway, we've determined weight and volume of buckets 1 and 2, empty. Now we need to determine the this volume is the same volume of sand that was removed, and you can use that to calculate the dry unit weight. So now we need to go get our sample. Let's go dig a hole. Okay, bucket number 1 is sand. Bucket number 2 is for the soil sample. So now let's dig. So that's probably about where it was to begin with. So now let's go back and weigh the difference. 35.4 pounds, volume of 3056, so inches cubed. So we never established what our assumptions were. So we need to assume water content of the sand, our void ratio of the sand, and then we really don't need this, how saturated it is. So this sand, I would say that's pretty uniformly graded, of varying particle size, and it was well drained. So when I Googled that earlier, that gave us a void ratio of 0.6, which is a ballpark number. Again, this is like a very back of envelope experiment, so we'll go with 0.6 for our void ratio, and our water content, we'll say is 10%, because that's a nice round number, and that's what Google told me to do. With all of that, that brings us to a saturated unit weight of 0.0582 and a dry unit weight of 0.0529. I don't think that's right. That doesn't seem right. There's no way that's right. However, this is more of the spirit of the experiment rather than the letter of the experiment. So we're going to assume that's correct, okay? Now we can go determine effective vertical stress. So first, we need to determine where our water table is. We were going to try a different strategy to determine if this was actually the water table. We're just going to assume that standing water right there is in fact the water table, which makes sense because it's pretty close to our test hole. So, come here. Eyeballing the difference between the top of the water and that hole.
I'd say it's like a foot.
A foot?
Possibly.
Okay, great. Good to know. This is dirty now. Okay, so our test hole is about, you about got stuck. See, this is why we're testing everything, so we can figure out how to fix this. So the top of the ground is about a foot above the water table. So we're going to plug that into our Excel spreadsheet and see if our pore water pressure is anywhere equal to the vertical effective stress a foot underground, and see if we are at or near quicksand conditions. So let's do that. Our water table is, so this row right here is our water table. So we have over here our dry unit weight of our sample. That's also in like inches per pound and not feet per pound. So that could be why. My unit weight of water is in pound cubed per, or feet cubed per pound, not inches cubed per pound. So, you know.
But if you had just spent a couple more minutes making your spreadsheet, maybe it would have been accurate.
I spent a long time making a spreadsheet. Okay, 0.0361 pounds per inch cubed. So after finagling some of my numbers, because I had my unit weight of water in pounds per feet cubed, not pounds per inches cubed, we had determined we are not at quicksand condition. We do have a positive vertical effective stress of 0.044. Again, I have no idea if that number is correct, but because we're in pounds per inches cubed because we're measuring everything in inches instead of feet, that makes sense. I guess. Sure, why not? So anyway, you can see right there, positive vertical effective stress. We are not at quicksand condition. So anyway, there is your at-home field back of envelope test of some of what we've learned in class this semester. I'm cold. Let's go back inside. Thanks for watching, and thank you to our cameraman. See y'all next time.